am Nurdin from UMPSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to Micro-credential module number 3, Timing Analysis and Design Optimization. In our first two micro-credential modules, we learned how to write Verilog code, simulate it, and synthesize it into gates. Now, it is time for the ultimate task, taking our designs out of the virtual environment and developing them onto physical hardware. Our overachieving goal for this module is to implement fully optimized digital system on the Altera DE10 Lite FPGA board, adhering strictly to industry best practices for code quality, resource management, and testability. Our journey begins with Chapter 9, where we dive into static timing analysis, or STA. Before we program the chip, we must mathematically prove that our design can run at our target clock speed. We will explore the critical metrics of system performance, the setup and hold times, mapping out the critical path, and calculating slack. You will also learn how to apply strict timing constraints using SDC file. We will put this theory into practice right away in Lab 6, where you will actively explore critical path and perform timing analysis on your own designs. What happens when your design fails to meet its timing constraints? That brings us to chapter number 10. We will diagnose common timing violations and their root causes, such as excessively long logic paths. More importantly, we will learn the industry techniques to fix them. Through lab number 5, you will get hands-on experience using pipelining, inserting registers to break up complex logic, and real-time to balance delay. We will wrap up this phase with post-synthesis verification to ensure our optimizations haven't altered our intended logic. Once timing is structurally sound, we transition to physical deployment in Chapter 11. Here, we will focus on high-quality RTL coding, specifically tailored for FPGA implementation. We will learn how to properly read quarters compilation reports to track our resource utilizations, keeping a close eye on our lookup tables, registers, and I/O pins. We will also master the pin planner to map our code directly to the DE10 Lite physical switches and LEDs. Finally, because physical hardware rarely work perfectly on the first try, we will cover vital onboard debugging strategies, including an introduction to signal tap logic analyzers to observe real-time signals inside the silicon. Everything we have learned culminates in Chapter 12, the final project implementation. This is your capstone project for this subject. You will be tasked with integrating all your previous developed RTL modules into one complete complex digital system. Your final mission is to achieve full timing closure, perform physical onboard debugging, and present a fully functional, optimized design running live on the DE10 Lite FPGA board, complete with professional documentation. By the end of Module 3, you will have evolved from writing abstract code to confidently implementing, optimizing, and verifying robust digital system on real FPGA platform. Let's get started. By the end of Module 3, you will have evolved from writing abstract code to confidently implementing, optimizing, and verifying robust digital systems on real FPGA platform. Let's get started.
Hello, hi. I am Nurdin from UMPSP STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to the make or break phase of digital design. Static timing analysis is the rigorous process of verifying that a design meets all timing requirements without the need for time-consuming gate-level simulations. It is the mathematical guarantee that your data arrives exactly when it's supposed to be, neither too early nor too late. In this chapter, we will bridge the gap between logical correctness and physical reality. The core objectives is to understand the golden rule, setup and hold time. The core objectives include to understand the golden rule, setup and hold time. Here, to understand the fundamental timing windows required by flip-flops, we'll explore why violating these leads to the metastability and glitchy hardware. And the second objective is to identify critical path and slack, meaning to identify the longest path in your design that dictate the maximum clock frequency. We will define slack, the safety margin between when the data actually arrives and when it must arrive. And thirdly, to apply timing constraint, we will learn the syntax and strategy of synopsis design constraint (SDC). You will learn how to tell the tool about your clock definitions, input-output delays, and false path to guide the synthesis and routing process. Why this chapter is extremely important is because a design can be logically perfect, but if the timing isn't close, the chip simply won't work. Static timing analysis is your final check before moving toward tape-out. In simulations, we assume logic gates evaluate instantaneously. However, real silicon obeys the law of physics. When transitioning a digital design to an FPGA, signal require physical time to propagate through logic cells and physical space to travel across routing wires. When transitioning a digital design to an FPGA, signals require physical time to propagate through logic cells and physical space to travel across routing wires. If we ignore these physical realities, a circuit that simulates perfectly will fail unpredictably on the board. First, we have gate propagation delay. Transistors are essentially tiny capacitors that need time to change and discharge. This creates a finite lag every time a signal passes through a gate. Secondly, we have interconnect delay. As our chips get smaller and faster, the copper wires connecting our gates actually becomes the biggest bottleneck. The resistance and capacitance of these wires, what we call as RC delay, meant that the physical distance between two components now dictates your maximum clock speed. Finally, we have clock skew and jitter. Because no two paths in a clock tree are identical, the heartbeat of your chip doesn't reach every cell at the same time. Our job in static timing analysis is to account for these imperfections. We use constraints to tell our tools exactly how much reality to expect, ensuring that even with these delays, our data always beats the clock. Before we can analyze complex paths, we have to define our heartbeat, the clock. When we talk about clock cycle, we are measuring the time from one specific point on a waveform to the exact same point on the next, usually measured in nanoseconds. This period is the inverse of our frequency. So a 20 nanosecond period gives us a 50 megahertz clock. Most modern synchronous designs are edge-triggered. The positive edge or rising edge is that critical transition from 0 to 1, while the negative edge or falling edge is the transition from 1 back to 0. In static timing analysis, these edges are our launch and capture events. If your data isn't ready by the time that edge arrives, the entire system fails. Understanding these basic coordinates is how we begin to map out our timing budget. Now let's zoom in. In a textbook, a clock edge looks like a perfectly vertical line. However, in silicon, an instantaneous change in voltage is physically impossible. We use the term rising time and falling time. This rising and falling time are used to describe the interval it takes for a signal to transit between two reference voltage, typically from 10% to 90% of the maximum value. The slope is what we call slew. Rising slew and falling slew matters so much to an STA engineer because a lazy or a slow slew rate doesn't just delay the signal, it makes the downstream gates switch slower too, dragging down the performance of the entire path. If your slew is too degraded, the signal might not even be recognized as a logic change. Mastering slew is the secret to controlling the uncertainties of your timing reports. Digital system speed is governed by strict timing windows. To avoid unpredictable failure, termed as metastability, data must be perfectly stable around the clock edge. The foundation of this analysis relies on two critical metrics: setup and hold time. Setup time is the minimum time data must be stable before the clock edge, and the hold time is the time it must remain stable after. It is the window before the clock edge where data must be perfectly stable. Hold time is the window after the clock edge where it must remain stable. Violating these windows will cause our flip-flop to capture unpredictable data. This causes metastability, leading to the system failure. To avoid setup violation, data must arrive and settle before the setup window begins. To avoid a hold time violation, the data must stay put until after the whole window ends. We consider the data stable only when no transitions occur during these critical periods. Now let's look at the shape of our signals. In a perfect world, a signal switches from 0 to 1 instantly, creating a sharp vertical line. But in the physical world of silicon, transistors and wires have capacitance that must be charged and discharged. This means every transition has a slope. We call this slope as the slew rate. Rise slew is the time it takes for a signal to transit from logic low to logic high, usually measured between the 10% and the 90% voltage thresholds. Conversely, fall slew is the time it takes to drop back down from high to low. Why does an STA engineer care about a lazy slew? Sharp slew led to fast, predictable timing. Degraded slews lead to timing uncertainty and increased power consumption. Managing these slopes is a key part of ensuring your design can run at high frequencies. Clock skews refer to the physical differences in the arrival time of a clock edge at different parts of the circuits. In an ideal system, a clock signal would arrive at every component at the exact time. However, real-world factors like routing delays and fan-out causes the clock edge to arrive at different flip-flops at slightly different times. Skew can be positive, where the clock arrives later than at the destination, or negative, where the clock arrives earlier at the destination, which can cause setup time violations. Positive skew is when the clock arrives later at the destination flip-flop, whereas negative skew is when the clock arrives earlier at the destination, increasing the risk of setup violation. Propagation delay is the time it takes for a signal to travel through a component. It is measured from the moment the input reaches 50% of its voltage to the moment the output reaches 50% of its voltage. The propagation delay measures the latency between two different pins, input and output. It is caused by the internal switching time of transistors and physical distance of the wires. So, for example, if you pull a trigger, a propagation delay is the time it takes for the bullet to hit the target. The maximum operating frequency, Fmax, is limited by the critical path, the route with the longest propagation delay between two registers. If the combinatorial delay grows too large, the signal will not arrive in time for the next clock edge, violating the setup time and corrupting the system. So this is the equation to calculate frequency maximum of a digital design. Minimum clock period is the shortest time allowable between two active clock edges. Clock to Q delay is the propagation delay of the source registers. The combinational logic delay is the sum of the propagation delays of all combinatorial elements in the critical path. The sum of the propagation delay of all combinatorial elements or gates in the critical path. The setup time is the minimum time the data must be stable before the destination register's active clock edge. And the clock skew is the difference in arrival times of the clock signals at the source and destination registers. It can be positive or negative. Let's take a look on an example of a maximum frequency estimation of a digital system design. Static timing analysis tools hunt for the critical path, the longest logic delay in our circuit, which directly dictates our maximum clock frequency. Static timing analysis mathematically evaluates every possible logic path in the design to verify if timing requirements are met without running a functional simulations. Using timing analyzers, static timing analysis checks for setup and hold constraint across all domains, the exact delay of the critical path, and the maximum achievable clock frequency, frequency max, Fmax. The tool then calculates our slack. Positive slack means we have safely met our timing goals, while negative slack means our hardware will fail. Slack is the margin between your required timing constraint and the actual delay of the hardware. If your slack is positive, your design safely meets the timing requirement. But if your slack is negative, a timing violation has occurred. To tell the STA tool what our timing goals are, we must apply timing constraints using Synopsys Design Constraint or SDC file. Here, we define our clock frequencies and input-output delays so the Quartus compiler knows exactly what targets it needs to hit. But how does the software know what our required timing is? We must tell it by applying timing constraints using Synopsys Design Constraint or .sdc file. Here, we define the exact clock frequencies and external input-output delays the Quartus compiler must target during synthesis. Constraint define intent. Violation report the reality. Let's look at a practical example. Adding two numbers. A simple ripple carry adder calculates sum sequentially, creating a long critical path. Recall our discussion in Chapter 5, Combinational Logic Design. In a ripple carry adder, the carry bit must physically ripple through 4 constructive full adders. This creates a long dependency chain. A 4-bit version might have a delay of 30 nanoseconds, yielding a frequency max of 77 MHz. This structure of logic design guarantees a slow critical path. In contrast, a carry look-ahead adder computes carry signal concurrently. By replacing ripple carry adder with a 4-bit carry look-ahead adder, carry signals are calculated in parallel using generate and propagate logic. The STA shifts dramatically. This parallel logic shrinks the delay to 7 nanoseconds, nearly doubling the frequency maximum to 167 MHz, proving that architectural choices heavily impact timing. This STA shift dramatically shrinks the delay to 7 nanoseconds, nearly doubling the frequency maximum to 167 MHz, proving that architectural choices heavily impact the timing of a digital system design.
Hello, hi. I am MC3 from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to chapter number 10, Timing Violation Analysis and Optimization. So, what do we do when our slack is negative? In this chapter, we will learn how to read quarters time quest report to diagnose the root cause of our failing path, which are typically caused by overly deep combinational logic. When confronted with negative slack and setup violation, we must find the root cause. Timing violations are most commonly caused by overly long or complex combinational logic path, excessive logic depth without any intermediate registers, poor routing across FPGA fabric, overly ambitious target clock frequency in which simply pushing the target clock frequency too high for the physical FPGA to handle. These consequences is a setup violation. The consequences is a setup or hold violation, leading directly to metastability. What happens if our design violates the setup or hold time? The flip-flop can enter a dangerous condition known as metastability. In a metastable state, the output of the flip-flop becomes undefined or unpredictable for a brief period. This ambiguity cascaded through the rest of the logic, ultimately resulting in a complete functional failure of the digital circuit. Because the input was caught in transition, the flip-flop cannot decide if it saw a 0 or a 1. Its output takes on an intermediate oscillatory or undefined value. This unstable garbage data then propagates to downstream logic, ultimately resulting in the complete functional failure of the digital circuit. So, when you encounter negative slack, you must optimize. To achieve timing closure, engineers rely on 4 main techniques: adding pipeline registers, optimizing logic expressions, utilizing faster hardware primitives, or rearrange the logic path or retiming. Our first major defense against negative slack is pipelining. By intentionally inserting flip-flop registers into the middle of a long combinational block, we break a massive, slow operation into several shorter, faster stages. This drastically shortens the critical path and boosts our clock speed. While this process takes multiple clock cycles to produce the first result, adding latency, it drastically shortens the delay of each individual stages, allowing the system's clock frequency to be increased significantly. Let's have a look in this pipelining example. Pipelining inserts immediate flip-flop to break long, slow combinatorial path into shorter, faster stages. It reduces the amount of logic to complete in a single clock, and it increases frequency maximum and throughput but introduces latency, more clock cycles from input to output. When the logic stages are simply unbalanced, you can perform manual logic rearrangement. By rewriting your Verilog to restructure heavily nested data path operations, you can distribute the workload more evenly across multiple clock cycles. In return, it flattens multi-level condition into simpler hierarchical decisions that evaluates faster. Moving or reordering logic operations helps distribute delay evenly across multiple clock cycles, eliminating single cycle bottleneck. It is being done by postponing complex operations to later pipeline stages, moving simple calculations earlier in the data path, and prevent any single clock cycle from bearing the burden of a massive calculation. An example of logic restructuring is shown here. This involves duplicating logic blocks to perform multiple computations simultaneously. FPGAs are highly suited for this because of their massive number of available configurable logic cells. While this drastically increases your resource utilization, it vastly improves overall data throughput. Another powerful optimization is avoiding the standard lookup table array altogether by mapping your design to the FPGA's dedicated hardware primitives. Modern FPGA contains built-in, highly optimized silicon structure like the digital signal processing, multipliers, fast carry chains for arithmetic, and dedicated block ramps. Routing your operations to these primitives provide the best possible speed. So do not build everything from basic gates. Infer dedicated silicon blocks available on the Intel Max 10 FPGA, for example. There are DSP blocks for fast multipliers, dedicated carry chain for arithmetic, and block RAMs for storage. Another optimization technique is retiming. If one logic state has a heavy delay and an adjacent stage is very fast, retiming allows the synthesis tool to automatically move the boundary registers forward or backward to balance the delays, smoothing out performance bottlenecks. In other words, retiming allows quarters to automatically redistribute existing flip-flops across logic boundaries. It moves registers backward or forward to combinational logic to balance delays without changing functionality. Retiming works by shifting registers forward or backward through combinatorial logic to minimize the critical path delay. It automatically balances the delay between stages, turning negative slack into positive slack. High-quality Verilog code is the foundation of reliable digital system design. While modern FPGA synthesis tools can successfully compile a wide variety of hardware descriptions, poorly written code often leads to inefficient hardware, unexpected simulation results, or difficult to detect functional errors. Good hardware description language design is not just about getting the circuit to function, it is about readability, maintainability, and predictability. Now, we will explore the 4 core characteristics of professional HDL code. It must be readable, modular, safe, and synthesizable. The first characteristic is readability. Because digital designs are complex and often worked on by teams of engineers, the code must be easy to understand for anyone reading it later, including the original designer. Professional HDL code achieves this through consistent indentation, meaningful signal names, and the use of clear commands to explain the purpose of specific logic functions. Clear code is the first defense against subtle bugs. Secondly, the code must be modular. Instead of writing one massive, intertwined block of code, professional designers ensure that each module performs a single, distinct function. For example, you should define separate modules for your adders, counters, and decoders. This modular approach not only makes the system easier to debug and test, but it also allows those well-defined components to be easily reused in future, larger systems. Third is safety. Safe HDL code intentionally avoids constructs that can introduce physical instability to the chip, such as race condition, metastability, or incomplete assignments that can accidentally infer unwanted memory latches. To ensure your code is safe, you must be exhaustive in your logic, meaning you must always specify all signal conditions and completely define your output within your always blocks. Finally, professional HDL must be synthesizable. Unlike traditional software programming, The ultimate goal of HDL is to create physical hardware. Therefore, designers must restrict themselves to using only constructs that map directly to actual FPGA hardware elements. You must strictly avoid leaving non-synthesizable, simulation-only features, such as time delays or display commands, in the code design that will be programmed onto the silicon. In conclusion, poorly structured Verilog code might still compile, but it will result in hardware that behaves unpredictably or violates strict timing constraints. By ensuring your code is readable, modular, safe, and synthesizable, you produce designs that are not only correct in simulations, but robust, reliable, and easily maintainable when deployed as real physical hardware. Before we move to the physical implementation, we used linting as our early warning system. It is a series of advanced static checks on our HDL codes that catches structural disasters before they happen. Basically, we are looking for things like unintended latches, which can ruin our timing later on, or mismatched bit width that would silently truncate our data, or floating signals and dead code, logic that serve no purpose and only at risk. By running linting tools early, we ensure that the RTL we hand off to the synthesis team is clean, professional, and ready for the rigors of timing analysis.
Hello, hi. I am Micro-credential from UMPST STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
With our timing close, Chapter 11 transitions us to the physical devices. We are finally ready to prepare our optimized RTL code for actual deployment onto the Altera DE10 Lite development board. Throughout this course, we have relied on simulators to verify our design in a virtual, idealized environment. However, as we transition to this phase, our goal is deploying our RTL, Register Transfer Level, code to physical silicon using the Altera DE10 Lite development board. The essence of this design process is device configuration. This involves translating our verified digital logic into bit stream, such as an SRAM object file or .sof file, which contains the raw binary configuration data required to set up the FPGA's internal logic, routing, and input-output structures. Once this file is downloaded via the USB blaster, your abstract code becomes a tangible, operating physical circuit. Before we can generate that final bit stream, we must scrutinize our RTL code. Hardware deployment demands strict code quality. Good HDL design is not just about getting a simulation to pass. It must be readable, modular, safe, and strictly synthesizable. Poorly structured Verilog code might still compile, but it often results in hardware that behaves unpredictably, consume unnecessary resources, or violate physical timing constraints. For instance, a common mistake is writing incomplete if or case statement. In a physical FPGA, this lack of exhaustive logic forces the synthesis tool to infer unintended memory latches to hold the previous state, which can introduce severe physical instability and timing bugs into your hardware. Once your code meets industry standard, the synthesis tool takes over to translate your Verilog into physical logic. Synthesis is the process of converting your high-level behavioral code into a gate-level netlist. Your compiler parses your code, performs optimizations like gate dead code elimination, and maps your operations directly to the physical primitives available on the FPGA fabric, such as lookup tables, flip-flops, and multiplexers. During this phase, it is critical to actively analyze the quarters compilation reports and address synthesis warnings. These reports will warn you if signals were dropped because they were unused, or if a latch was accidentally inferred due to an incomplete sensitivity list. Another crucial aspect of analyzing the compilation report is tracking your resource utilization. Unlike software running on a PC, an FPGA has strict physical space limitation. The Intel Max 10 chip on our DE10 Lite board contains exactly 50,000 logic elements, alongside a finite number dedicated registers, block RAMs, and input-output pins. You must continuously monitor the resource utilization section of the fitter report to ensure your design actually fits on the chip. If your design is too large, you will have to iterate your RTL code, perhaps by sharing resources or optimizing your logic to reduce the physical footprint of your hardware. We must map our abstract Verilog variables to the real world using the quarters pin planner. Your Verilog code defines top-level input-outputs, but the FPGA does not automatically know where the signals should go. The pin planner is a spreadsheet-like interface where you assign your software signals to the exact physical pin coordinates of the DE10 Lite board. For example, if you want an output to control an LED, you must assign it to a specific pin like pin A8, or map your input to slide switch or pins like the pin C10. This step is the literal bridge between your abstract code and the physical interfaces of the board. Once programmed, physical hardware rarely works flawlessly on the first try. Real-world physics introduce new bugs. For example, physical switches exhibit bouncing, rapidly flickering between states for a few milliseconds when toggled, which requires dedicated debouncing logic to stabilize. To troubleshoot these hardware-specific issues, we rely on basic on-board debugging strategies. A fundamental design for testability (DFT) technique is creating physical props by routing critical internal signal, such as the state of a finite state machine or the value of a counter, directly to the board's external LED. This provides a first-level X-ray into the chip, allowing you to visually monitor internal operations in real time. When simple LED probes are not enough to catch complex high-speed bugs, we turn to advanced tools like the Signal Tap Logic Analyzer. Signal Tap is an incredibly powerful on-chip debugging tool that acts like an embedded virtual oscilloscope. Instead of just routing a few signals to LEDs, Signal Tap is compiled directly into your FPGA hardware, allowing you to capture, monitor, and trigger on hundreds of real-time internal signals while the chip is actively running. It enables deep-level visibility into the silicon without needing to alter your RTL code or wire up external physical oscilloscopes, making it an indispensable tool for achieving final hardware verification.
Hello, hi. I am MC3 from UMPST Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Hi, welcome to Chapter 12, your final project implementation and review. The first phase of project implementation, or the capstone, is system integration. You will take the individual RTL modules you developed throughout the course, like your finite state machines, your debouncers, and others, and integrate them into one unified top-level architecture targeted for the DE10 Lite. The second phase is achieving final timing closure. You must run full static timing analysis on your integrated system. If integrating the modules created new critical path, you must debug them and apply pipelining until the entire system operates with zero negative slack. Then proceed to hardware debugging strategies, where you should verify your clock domains, check your pin constraints, and check the on-chip logic analyzers. The second phase is achieving final timing closure. You must run a full static timing analysis on your integrated system. If integrating the modules created new critical path, you must debug them and apply pipelining until the entire system operates with zero negative slack. Finally, adhering to the industrial standard for quality and testability, you will finalize your project with professional documentation and live presentation. By completing this, you will have proven your ability to implement optimized, fully verified digital systems on modern FPGA platform. Thank you and good luck.